Okay, welcome back. I think we'll go ahead and get started. And I will record this on Zoom, so I will put that on. I'll just record it as one whole one continuous, and I'll upload that to the YouTube where I'm uploading the lectures. And so we've got 7 talks, about 7 minutes, including Q&A. So I figure sort of 7, 8 minutes, and then a couple minutes for that. Anybody that abuses it, no dessert. So anyway, but we'll start with Vivian Bhat. So Vivian, yeah. So I'll turn it over to you. Yeah. Okay.
Everyone, this is Vivian, and I realize that this title is a mouthful for a 7-minute talk. So I am originally a theorist. I mostly work in BSM, model building, and Pheno. But this is something that I got into because, well, my advisor told me to. But it's actually been pretty cool. It's something I've been doing over the last few months, and it's kind of fun. So with Hilumi coming up, precision searches are becoming more and more important. And one of the first problems that we face before any analysis is a combinatorial problem. When we have a ttbar Dilepton event, you have 2 B quarks, 2 leptons, and some missing ET. Now we can't identify the correct combination of the B and L, like you have B1, L1, B2, L2, and pairing them up properly is not as trivial a task as it might seem. There are a lot of cuts and with cuts based on momentum information, on geometrical distance, and using the rapidity and stuff that do help us figure out which is the correct combination. These cuts have very high purity but very low efficiency, as we saw earlier today. So we lose out on a lot of data because we just can't tell. As you see over here, this is just one of, so we use multiple high-level kinematic variables. This is just one example of the invariant mass, which is like the most vanilla of them all. So as we see that you can correctly identify the incorrect combination beyond 170 GeV, but for anything under that, we can't really tell. So obviously, as with all things, we use machine learning. That's pretty common these days. And again, I shall point out good is to the top left corner. So anything that's closer to 0,1 is good. That's the ROC curve. AOC is something that I'll refer to. That's just the area under that curve. The closer it is to 1, the better it is. So here we see a score distribution for the correct and incorrect combinations. This is a log plot, so it actually does much better than it looks over here. But we see a good separation between the correct and incorrect combinations. Now, my favorite slide in this whole talk, and I will pause here. So machine learning is essentially just a bunch of linear algebra soup that you're just stirring it till it looks right. And where there is linear algebra, we can use quantum algorithms, because what is a quantum system but just a nice Hilbert space for some linear algebra? So the universal approximation theorem from machine learning also translates onto a block sphere for quantum algorithms, and we can actually utilize that for doing a lot of machine learning applications using variational quantum algorithms. So instead of a network with multiple layers, you sort of just push your deep neural network onto its side, where each neuron in your neural network is a rotation gate acting on your qubit. And one of the cool things about this method of doing things is we use something called angle embedding, wherein each of our data points is each data point is essentially an angle that goes into our Pauli matrices for the rotation. So if we start with anything on the block sphere, we have a state vector that's, say, we just start anywhere along the equator, apply a bunch of rotation gates, it keeps rotating around. The rotation gates have the data input and are also parameterized. So we can essentially use an observable such that anything in the northern hemisphere is a correct combination, and anything that ends up in the southern hemisphere is an incorrect combination. So we can build a binary classifier using just one single qubit. So it's a very straightforward and easy quantum circuit where there's not, it's called quantum machine learning. It just sounds like a bunch of buzzwords thrown in together, but it's nothing but one single two-state system with a bunch of rotation gates applied to it. So this is the simple proof of concept test that I did on this. With 3 kinematic variables, you get an AUC of 90%, which, as anything close to 1 is good. The neural network had 97, but this does have 90%. The one thing that's better over here is that there is an endpoint for the correct distribution, which the neural network was not able to correctly reproduce. So this does seem to learn better, and it actually learns much more quickly. Now, the one main thing that we hear about quantum algorithms is that they're much more expressive than normal, your plain deep neural networks. And this is just a scan over the number of parameters in the circuit and the number of training samples, where you see, I don't know, can you see? For the neural network on the right, it goes from 0.05 to 0.95. And the quantum network seems pretty stable for even as little as 20 parameters and 250 training samples. You still have an accuracy of well over 80–85%. So it's much more expressive with limited data and with limited number of parameters. And why this is of interest to us is that, especially when we're looking at rarer events, say something at Dune, we're not going to have the 100,000 events, 100,000 trustworthy events that you would need to, train a neural network that could actually do any good. So in such contexts, having a quantum algorithm would actually be more beneficial, and these also train much faster. The one in orange is the performance for the quantum network, and blue is for the classical one, and we see that it's actually learning much faster. Here, of course, we have used just the 3 kinematic variables, which are high-order features. So it's a relatively simple learning task. What I have done since is that we're trying to just give it the momentum information in a Lorentz invariant way and try and help the network learn what the physics is. So I'm using a 2-qubit system and imposing the topology of our event itself onto the 2 qubits, where each qubit sort of corresponds to a top quark, and you feed in Lorentz invariant quantities that are not high-level variables, just your low-level kinematic momentum products. And it does pretty well, but it's still a work in progress. So that is what I want to do now, because right now we're just giving it ready-made variables that don't really capture all of the physics information, but we want to know what the network learns. And we want to know if these variables that we've chosen are actually the best variables to capture the physics of the problem. Because, I mean, sure, we can tell whether it's a correct or incorrect combination, but this would hopefully help us actually understand what the best choice variable is and understand the physics behind the classification. So, yep, thank you.
Yeah. So for your neural network, are you using the bunch of neural networks, or are you just doing?
No, it's just a very simple deep neural network with very limited parameters for this kind. Yeah.
Is this seen as like an analysis tool through offline, or are there any projects that are used like at the high level?
So this analysis that I've done is with the Parton level information, but I'm planning to do the detector, add the detector smears and do it later. So to me, a B quark is just a B quark. It's forgotten. I know I'm not the QCD school, a little out of space here, but the B quark is just the B quark. That's very simple system. Yeah. Yeah.
Is this for a
Yeah.
So how does that compare to if you just do So you can write down the kinematic equation. How does that
Yeah.
compare to?
But you do have a lot of missing energy, right? So you can't, you have your two neutrinos from that accompany the electron, so you can't analytically identify the correct information. You need, like traditionally, you apply cuts based on the invariant masses and the like separation between the two.
So I think there's some ways that he was like, you can solve the equation and then you can, obviously you don't have the math, but we can
Right.
pick the solution that maximize something,
So-
or the one that's closest to the.
Yeah, so I believe there are some methods that we actually assume that the W goes on shell or that the top was on shell that helps us. Like since we don't have the missing ET, we don't observe the neutrino. So there are some methods that assume that the W or B is on shell, but again, that imposes some additional constraints. So I mean, those methods are tried and tested and work really well, but they're not very efficient. So we do end up losing a bunch of events to those assumptions. They have excellent purity, but not very efficient.
I probably missed it, but how are you classifying what's incorrect?
So you have a block sphere, a qubit resides on the block sphere where you have 0 and 1.
The first one that you put.
Mhm. As in,
I just want to know what's correct and.
yeah,
Yeah.
yeah. So this is just the invariant mass for the BL system, where the red one is the distribution for the invariant mass for correct combinations, and blue one is the incorrect one. So this is like one of the many variables that are used. You impose cuts on all of these variables and, cut it down quadrant by quadrant to get.
Right. So how do you go from incorrect to correct? If you're trying that's on your problem.
Yeah, so as in you have two B quarks, two leptons.
Yes.
You don't know which one pairs to which.
Yes.
So right now, oh, you're asking how I know which one is correct, which one is incorrect?
Yeah.
Oh, this is data from Pithia. I mean, like I'm giving the correct label and I'm training my network on, the actual data. So that's how I know whether it's correct or incorrect. But all of the performance I showed is on training, is on testing data that the circuit has never seen before. But again, I know what it is, so that's how I'm able to identify whether it's correct or incorrect.
It's
Alright.
Hi, I'm Brandon. I'm a graduate student at SMU. I'm working with the Surge Global Analysis Work Group with Fred and the postdoc Peter. We also have two very talented graduate students, Rebecca, who's here, and Janae, and I'm also a part of it. We're a part of CTEQ-MCgen, and our main group is the Surge group. I figured we'd talk a bit more about Surge at this school. So all you really need to know is it is dealing with gluon saturation. So when you're studying gluon saturation, you do this. You do this by studying the structure of the proton. You've seen that there are two different ways you can do this: the Parton model, which we've discussed in some detail, and then there's the dipole model. We decided to just do both and make a work group that can analyze the differences between the Parton model and the dipole model. Right now, we prototype this in a very simple Python notebook that is able to take in data from various generators or codes that other people have done, and we can compare the results. We do this by looking at the sigma total function, where our code takes in a wave function and a scattering amplitude. We can then grid this. This is not Lattice QCD, we just gridding this so that we can then do a convolution to get our sigma total value. And then from that, we can calculate any parameters you would want, such as we have to our FL functions. We eventually plan to be able to calculate the chi-squared and plug it into XFitter to open up a large range of analysis. Right now, we have some preliminary results here. Both of these are shown for what's called the BK model. These are actually the same model. We have two different models in testing. One just takes about an hour, while the BK takes about a minute. So we're testing it all on that. The black dots here are the para data. So we have pretty good agreement along some parts. For the others, we're trying to figure out if it's our code that's wrong or the BK code that's wrong. Now, when we say this is a global analysis framework, we want it to be global as in for the community. So if anyone in here is doing any work on gluon saturation, we would love to hear from you. We'd love to have an idea of what you're doing, what kind of analysis would help you in your research, and how we can make a tool that will be used by your group and how we can make your life easier. So feel free to email myself or Fred, and hopefully we can make a great tool that will just make your life easier in the future. Thank you.
Questions about that?
That's such a good job.
Could you take it back one slide, please? I was worried about the window shaded region.
Oh, the shaded regions are unphysical regions because basically we know it's just that's nonsense data right there. We just can calculate it and then code it so we know that, and we shade it to signify that it's unphysical. What's up?
Why?
If I wasn't up here, I have no answer. Why is it unphysical? It's just the accuracy range, right?
Well, it's outside, I mean.
Yeah, it's outside the kinematic range. Yeah.
Don't think it's shown that, yeah, well, it's in the small factor.
What is the answer?
Oh, it's just, it's outside the kinematic.
It's like not on physical, just the
Yeah.
Yeah.
I mean, when you look at the XP plot, there are cuts of what you can measure, and that's, yeah, you see the data points, the black is the real data points, and they run out of gas for the different variables. And like, you know, what's fun here is, again, you know, so this is a complementary way to the Parton model, and by comparing them, you're picking up different pieces of, you know, perturbation expansion, kind of like I talked about hallucination. So by comparing that, you know, this is supposed to do a better job in small X regions, so we'll try that out in the SE.
Yep.
Other questions for Brent?
Yeah.
So just to make sure, the blue and the green lines come from a model or?
Yeah, they're actually the MD gamma model for the Parton, so the BK what's the whole name of it? Yeah, I just call it the BK model with MD gamma parameters.
What's the difference between the two?
The parameter C, which is essentially a scaling factor that goes into it. We're just testing out a few different parameters, and this is a plot I had that I could add to the slide. We have various other plots that compare the two different models between the Parton and dipole, but all of them basically come out that they're the same as we would expect.
Let's thank Brandon again. One comment, so, behind the scenes, you saw Brenda, who was taking the picture, this afternoon. She's been doing all the work to make sure you get fed and have a place to, sleep at the dorms and things like that. So I just, you know, when I send around a card, if you sign it, go ahead and sign it. There's room for a small note. I'll pass this around. And if everybody could just sign it, we'll pass it on to but did want to acknowledge that she's been very instrumental in making this work. So, okay. Let's see. And let's see. So I think is this uploaded now? There it is. Okay, I think. All right, what's that?
Thank you for giving a chance to do the contributed talk to get some travel support for. Thank you, Professor Fred Honest. And today I'll just give a 5 minutes talk about on a small part of the factorization of the Fermi function and the precision QED corrections to the neutron lifetime. So I just talk a little bit of part of in this project is the factorization of the Sirlin-g function. And I just realized my slides is more about the computational details. So maybe this is not so good. And thankfully, this project is in collaboration with my advisor, Richard Hill, and Ryan and Peter. They are postdocs at Caltech and the Fermilab separately. The motivation to investigate the Sirlin-g function, since the Sirlin-g function describes the QED radial corrections at the leading order to nuclear beta decay, which is introduced by Albert Sirlin the first time. And the Sirlin-g function is a model independent since it describes the radial corrections between the outgoing electron and the proton, so it should be universal. It's not related to the nuclear models. And the importance of investigating the Sirlin-g function, it provides a precision test of the physics beyond set model and determine precisely the CK and matrix element BUD. This is the three diagrams. Since the Sirlin-g function is in the leading order, so we only need to consider the one loop diagrams. The first diagrams is just the virtual corrections. The other two graphs are the real radiation corrections. And the first graph, the single line means the electron, and the double line means the proton. And if you're just using the QED Feynman rules, and you write the amplitude, and you can get the cross section or differential cross section, which is the delta. And here is the hard means when we do the phase space integral over the phase over the photon, which is E gamma, you just pick this color. The delta E is the lower bound for the photon energy, and expand the final result, the delta E over E. The big E is the energy of the electron, and you will get these two expressions. And you can see we have the two scales here, which is mu h and mu soft. Remember here, the 2 pi square over the beta, this term here comes from the, here we call this diagram is time-like procedure. Is equal to the space-like procedure by reversing the velocity of the heavy particle, the velocity v to the minus v. And this 2 pi square over beta can be viewed as the final state the electron interacts with a background field. So the total hard contribution is the sum of the virtual hard differential cross section plus the the real hard the real hard cross sections. And similarly, we can calculate the soft photon contribution, which we just changed. We need to use a photon mass regulator, which introduce the photon mass, which is lambda, and integrate over the photon energy less than the cutoff, the delta E. And similarly, we can get the total soft photon contribution. So if we sum of the hard and the soft, we can reproduce the Sirlin-g function by setting the hard scale to the mass of the proton. So we just translated the Sirlin-g function into the modern MS bar language. And here, next I will talk about in the small mass limit, the virtual corrections. There might be a typo here. It should be the hard differential cross section. So here the MH, I just use the different notations. Here it should be the delta H. Here MH is the delta H here. This is the original Sirlin-g function from the Sirlin's 1967 paper. So if you plug in these two expressions, and amidst the 2 pi square over the beta term, this hard virtual amplitude of the differential cross sections can be expanded to this expression, and we set the mu s and mu h to nu mu. And on the other hand, we can see the new hard function, which is fh, and new jet function fj, and we just prove this are equal, which means the hard virtual amplitude can be factorized a new hard function and a new jet function. And this is what I.
Why didn't you can say that your soft and hard scale are the same value? When you took them both from you?
Yeah, I think that's a good question. I might need to think about it.
Okay.
After, yeah.
I mean, in the various lectures, we talked about running the alpha S, and but also the other constants run. I don't think we've shown here, but the rather interesting plot is the unification of the couplings, where alpha S is something over log of log of the energy scale. If you plot the inverse on a logarithmic plot, it's a straight line, and then if you put the QED and the QCD together, you get a unit. I mean, they almost cross, depending on your model, out of some high unification scale. And so, having this to high precision, these kind of things at high precision helps you make those predictions. So, yeah. Have you looked much at all at that? Or is that sort of in the back of your mind at all? Or?
I didn't think too much about that. Yeah.
No, I mean, it seems it's kind of important for stuff like that.
Yeah. I think it's for the precision test. Yes.
Other questions, comments? Let's begin. So.
Download the new PPT, I have already made something.
Sorry?
Can you download the new PPT? I've made
Oh,
something.
okay. Give me a sec.
The fourth one.
Um,
Right.
Thank you, Brett. So, hello everyone. I'm going to present my work about jets. So we have already had some sessions on jets, but more is about to come. So this is my work about how jet evolves and how is the dynamic inside jet when it is passing from the PVP state, is a partonic plasma state, to the hadronic state. So how is the dynamic, what kind of changes happen there? This is my work done with my advisor, Abhijit. We are part of a collaboration, Jetscapes. So there is effort from other people as well. So starting off with this jet, if we take a system like PP, it's not made up of that much material. Of course, we know that we had a lot of things like proton is made up of up, down, but if I compare it with respect to lead, then it's nothing. So if I take around 5 kilo energy, make the proton proliferation, QGP is not formed. Okay, but if I take lead, then a QGP is formed. And when I have, so in this collision, there are some scattering which are very hard in nature. Hard as in there is a lot of transfer to metal transfer in that. So a jet which is formed and then it is passing to this QGP tends to lose a lot of energy. That's why quenching. So if you see, I have taken three conditions like 0 to 10, that's like photon collision. 60 to 70, that's like brushing upon each other, like this peripheral collision. If you see that in 0 to 10%, the amount of QGP that is formed is large. You can see a lot more quenching with the purple points. This is data from the Atlas. 5 p energy, if you take 60 to 70%, much less quenched. So where we are going with this RA plot, yeah, so this is actually the ratio of the differential cross section of lead to PP. So you can see some quenching in there. Jets, when jets are formed, jets are not formed isotropic in the azimuthal direction. If so, this is the plot from CMS when in the central collision. In the central collision, almost head on, you can see that the distribution of jets is almost isotropic. But if you take a peripheral collision, like in this case, this is also from CMS, the yellow points are the charged part, charged tracks, the blue and the green are the H car and P car data. You can see that there is this forms an almond shape. So the jets, if a jet is going along the short direction, okay, it has much less PVP traverse. So it will going to lose much less energy. Compared to a jet, it is going along the longer side. So that's the place from where the anisotropic and the jet distribution is coming. How do we quantify it? We plot differential of M with respect to V5 jets. Phi is event plane. There is some fancy method to find the event plane. And we try to Fourier expand it. There are different terms, V0, V1, V2. We are interested in V2. V2 captures the idea of how much path length dependence the jet has. V1 has to do with if my jet is affected by the longitudinal fluctuations in the initial collision. But in our model, we take everything to be boost invariant. So V1 goes to 0. It's only the V2 that we care about. In order to study all this, we are using a Monte Carlo approach. Using a Monte Carlo, just like PTR, it's Jetscape, but it's much more versatile. We can do everything. We can have initial state radiation. We can have a collision. We can have free streaming. After some time, it thermalizes from the QGP. There it follows the relativistic hydrodynamics equation to evolve. Just go through that QGP, loses some energy. Everything hydronizes at some point. There is hydronic transport as well. It's a versatile model. It's modular extensible. If you want to put in more physics, we can simply put in more physics without changing anything else. It's publicly available. You can go to GitHub and download it. So what I am interested in is in the middle region, shown by the blue region, where all of the jet energy loss dynamics is handled. So we learned that when the Parton is making a cover, it is ordered in virtuality. So what we do is when the Parton is extremely high in virtuality, it's in the red phase. We follow a model, we make it deglapp, we do deglapp evaluation to model that evolution to model that part of the shower. But this is not the normal deglapp because there's media around. We do some modifications. We are using a modified deglapp to make the evolution. After some time, it loses a lot of virtuality and it enters a very dense region. Okay, so there is a lot of quenching. That part we are modeling with linear Boltzmann transport. Why are we doing it? Once the virtuality goes less than 2, less than 4, what happens is the number of elastic scatterings are much more with respect to radiation. So that brings in the LPM effect. What LPM effect does is, since there is so many elastic scattering, the Parton doesn't get that much time to radiate. It faces quantum interference. So what I'm interested in is to study, if you model this region where it enters a low virtuality phase. So what we do it, so this is the starting part, the equation that you see, that's the linear Boltzmann transport equation. As I said, there's LPM effect, and since my Parton is entering a low virtuality region, it has also lost a lot of energy. So we cannot take a constant alpha. So we take a running alpha. We are considering all this kind of, we are trying to model all these different kind of diagrams that are possible. So there is scattering happening, radiation happening, all different things. The good thing about Jetscape is, unlike PCR, which does all the evolution in the momentum phase space, Jetscape does it in normal space-time coordinate. So you can capture position, where the split is happening, at what time it is happening. So as I said, when it enters this linear Boltzmann transport space, it has two things. One is Soto to elastic scattering. So this is the elastic scattering kernel. You can see F1, F2, those are like the distributions of the entering Parton, the outgoing daughters. Then there is F2. F2 is my the distribution of my media. In most cases, we take it as Boltzmann line with Fermi statistics and both statistics, but we are trying to put some modification in it as well. And you see that there is a matrix square element. For our case, we are just taking the 3-level diagrams, the different SCU channels, with Quark, with Gluon, with Gluon. There are, I think, like 20 sets of different possibilities from where you can get the matrix elements for it. The total elastic rate probability is given by the sum of all the different type of 2-to-2 processes that could happen. Like for Quark and for Gluon, there are two different rates. Along with the scattering, there is radiation as well. So using the higher Twist formalism, we have this differential Ng. Ng is the number of gluon that is radiated. Dx is the momentum fraction, K third square, you can understand it, dt is the time. You can see on the right hand side, there is some Casimir factor is there, Q hat, I'll come on what Q hat is. So we are using some sampling models to guess what is the probability of like how many gluons to be radiated in one time window. So this is taking care of the radiation part. As I said, the probability of gluon radiation is given by 1 minus E times this thing. In every time window, we also take assumption that the scattering probability is Poisson-like. So it could be only one scattering or no scattering. Like to make a distribution, the probability of having 2 scattering, 3 scattering, if you take a sufficiently small time, the probability goes to 0. So we are just consider one scattering or no scattering. Okay, so you see the model, what all is happening in the radiation part, in the scattering part. But in order to quantify how much quenching the jet is facing, we need a variable. That variable is Q hat. Q hat is the amount of transverse kick the jet is getting from the media around per unit length. So in the transverse square. So Q per square is the kick from the media. Lambda is my mean free path of the Parton, so the length between two collisions. If you have some leading order calculations, we find out this is how the analytical thing comes out for Q hat. which is shown also in the green plot. So you can see that Q hat upon T cube, this is a dimensionless quantity, it just goes up with temperature. But the HCl formula breaks after some temperature. I think it's like 200 MeV where the HCl formula breaks. So we need a new way to extend our Q hat plot. So there are some new calculations from Lattice, which found out that if you go to lower temperature, this is how the Q hat plot looks like. So these are some of the results from Jetscape. These results use the Q hat, which is shown in the green line. You can see that for 0 to 10%, we are doing an awesome job. You can say that, of course, in the high PT region, the array is not totally matching up with the Atlas data, but there's a discrepancy between the experimental data as well as CMS and Atlas. We are able to match the pin points. So for 0 to 10% in the central collision, we are doing an awesome job, but when we are going to peripheral case, 60%, you can see that we are a lot away from the experimental data points. So the hypothesis is something like, since in 0 to 10%, the media is much bigger, the volume of the QGP is much bigger. There is no partonic and hadronic interaction. But in the case of 50 to 60, the media is very small. So there could be some partons which still have enough virtuality to radiate in the hadronic phase, and they can also scatter. So I'm trying to model that using all this Boltzmann model that I just showed.
Like 2 minutes.
Okay, yeah, I'll be done. So I'm trying to use the extended Q hat, since I need this extended Q hat because when I'm going to the hadronic phase, I'm at much lower temperature. So I'm using that Q hat, and I'm using radiations and having 2 to 2 scattering when I'm entering the hadronic phase. After including them, I find that the 0 to 10% plot, the red one is with inclusion of this partonic and hadronic impression. I'm doing much better, but the real good thing is when I'm going to 50 to 60%, I'm much more closer to the experimental data. It's showing that there is, of course, some features of partonic energy loss in hadronic phase. The real variable we are looking at is V2. I'm done. This is last slide. Yeah. The real thing I'm looking at is V2Z. These are the results from the Jetscape. I'm still working on getting the other V2. That's all from my side. Thank you. Sorry for being over time.
I'll ask you offline about the Jetscape. Yeah, I'm curious to see how that goes. So that's an interesting project.
Yeah.
Oh, very good. Thank you.
Yeah.
Okay.
Thank you.
Let's take it again. So. All right.
So usually when you think about the length of the, between 1 minute per slide, right? So you have 90 moles on lunch.
Oops. All right. Okay, all right, Alex. And I have you guys in the right order now, yes? Okay.
All right, hi, my name's Alex. I'm a first-year grad student here at Michigan State University. I work under Dr. Lin, and I wanted to talk about Lattice QCD today because we don't have any lectures on this topic, and I think it's kind of important that you go away knowing something about Lattice QCD. So I'm going to introduce this briefly, and then in the next talk by Bill, say hi, Bill. Bill's going to talk about Parton distribution functions in the Lattice. So this is a super quick introduction to Lattice QCD. So first off, we know we can compute observables in the continuum QFT using the path interval formalism, where this S is our Minkowski, and the integral is over all possible configurations. But if we try to compute this numerically, we run into an issue called the sign problem, where this oscillating factor introduced by the exponential causes these configurations to cancel out. And so we can get around this problem by doing a Wick rotation, and this rotates time into the complex plane and converts our Minkowski action into the Euclidean action. So now the weight, this exponential, behaves like a Boltzmann factor, and so we can treat this probabilistically by sampling the field configurations. So now that we have a problem that's numerically feasible, we need to set up our lattice, and we can do this by discretizing space-time into a 4D Euclidean grid, where we have these quarks living at what we call the lattice sites and our gluons on these gauge links that connect these neighboring sites. So there are three main parameters that we can vary to control systematic uncertainties. And unfortunately, I have to kind of gloss over these quickly for the sake of time. But they're going to be lattice spacing, volume, and pion mass. So the lattice spacing determines how finely or coarsely this box is discretized. And this is not something that we choose, but it's something that we determine through a process called scale setting, which is where you set the bare coupling and compute some experimentally well-known value and then determine what the lattice spacing is by comparing our numerical result to this experimental result. The volume is essentially how large of a box we're simulating in. The main thing here is that we want to make sure that our box is large enough that we don't have any overlap at the periodic boundaries from whatever we're trying to put in our box. And then finally, the pion mass, this basically gives us some control over reducing the computational cost by allowing us to simulate heavier than physical pion masses, which are a little easier. So now that we have our lattice theory set up, we have our box with our quarks and gluons, we can generate these gauge field configurations. And since we can't possibly integrate over an infinite number of configurations, we use Monte Carlo methods to sample these. So in this funky figure that I have up here, the amorphous blob, it represents the spacefall configurations. Each little black dot is one gauge configuration, and then the black lines kind of show the Markov process connecting these, visiting each one sequentially. So again, these configurations correspond to possible QCD vacuum states, so like snapshots that contain fluctuations of the gluon field. And we want to use these because we compute our observables on these configurations, and then we can take an average over this ensemble of configurations that we have to get some final value with some statistical error. And we don't have time to pause for a quick recap, so I'm going to move straight into an example. So say we want to compute something really simple on the lattice, like the ground state energy of a nucleon. We can define this nucleon interpolating operator and give it the same quantum numbers as the nucleon that we want to put on the lattice. So here we have A, B, and C as our color indices. Alpha would be our spin index. C is your color conjugate matrix or charge conjugation matrix. And we have some undefined quark flavors here. So what we would do is we would put this interpolating operator somewhere on our lattice at some, say, initial time t equals 0, at some spatial time 0. And we would allow it to propagate for some time before we annihilate it. And this defines what we call our 2-point correlation function, where these kets and brawls are going to be our QCD vacuum state. And we use this projector to project out the spin degrees of freedom that we want. So say we do this, we compute these 2-point correlators across all of our ensembles. What do we do with all of this lattice data? We can rewrite this 2-point correlator by inserting this identity matrix, and we get this infinite tower of states. And you'll notice that at large times, the ground state term is going to dominate. And so we can approximate this 2-point correlator using these first two terms. And so what we can do is we can fit our lattice data to this model function, and we can capture the ground state energy, and then we have the excited state energy to capture any contaminations. But we calculate a lot more than just ground state energy on the lattice. I have just a couple examples here. If you want to learn more about other things that we can calculate, I would recommend you to read this flavor lattice averaging group or FLAG review. This covers the strong coupling constant, CKM matrix elements, etc. Everything but PDFs, which is what Bill is going to discuss next. And that concludes my super quick introduction on lattice QCD. If anybody has questions, they can go ahead and ask them now. I also have resources here from student to student I found useful.
So one problem is that it necessarily generates both left-handed and right-handed neutrino at the same ratio. Is that still a problem?
I don't know anything about neutrino lattice calculations. Sorry. Bill, do you know anything about those?
No, that is true. It's
Yeah.
Question about the way you like to use it on things. Yeah, so you have the three quarks, I guess. Why is gamma there?
I'm sorry, why is?
Gamma
Supposed to. I'm sorry, I'm not sure I follow the question. Why is gamma 5 there?
And why do we have them? I'm supposed to say the brand is supposed to project some of the. Are you doing question?
Mhm. Yeah,
So, this is,
yeah.
right, we can get my players in principle, and, as long as they have the same quantum number, so, beyond, I don't know if I can.
Okay, so if I understand up to the difference between them, so you from one part to the one seven. Alpha on the left hand side is on the one part of the right hand side. You just put one or two seven one.
Oh, you mean that one? There's only five.
I think that's the not fine, because. Everything is something. Yeah.
Why does this one?
Probably feels like the, nothing.
No, you know, it's feeling like it's only on one quad.
Yeah. Different power.
Let me just add that usually we would have a lattice component to these schools. In fact, we'd ask Leila Lynn to do this. She's, of course, she's here local, but she's also the CTEQ spokesperson and also the leader of the PDF lattice group, which is looking at the interface of, using the lattice results for PDF. But unfortunately, because she's out of town, that didn't happen, so we appreciate that. We still do the interface. So, let's thank Alex again. Then I guess we'll have a follow-up by William, so.
Let's see if this is super fast or not. I might ramble.
Yes.
All right. Thank you. My name is Bill Good. I'm a fourth-year grad student here at MSU. I'm working on Parton distribution functions from Lattice QCD, specifically the gluon. So I hope from the lectures this week that you took away maybe this definition of the PDF. So you can define the PDF as the Fourier transform of this type of light front correlator here with separation along the light cone direction Z minus. And there's a Wilson line for gauge invariance. Wait, I want to hide that. I don't want to spoil it first. So you might be asking, we're working on a Euclidean lattice. How do we measure something that is on a light cone? The light cone is a single point when you're working with Euclidean space. So some people smarter than me figured out that very roughly speaking, you can take your correlator in the spatial Z direction and take the hadron states to be to have large momentum. And you can see with the red line, that starts to boost your correlator towards the light cone. So you start approaching this light cone as you increase the momentum. You'll also notice that at very short distances, you're also pretty close to the light cone as well. So this kind of defines these two different methods called large momentum effective theory, which I'll call LAMET, also the quasi-PDF method, and the pseudo-PDF method. So the quasi and pseudo PDF methods both start with the same Euclidean matrix elements, and they have to have the same light cone behavior as those PDF matrix elements that I was talking about before. So when you take this large momentum or your short distance limit, this limit does not commute with taking the UV cutoff to infinity. It's like a very non-trivial statement, but basically what that means is that with some other things included, you can do perturbative matching such that you're obtaining a good approximations to the light cone physics. So with the pseudo PDF method, you can take these lattice matrix elements, which I drew with the script M on the left, and you can relate those to, this is a gluon PDF, for example, to a convolution of the gluon PDF with a perturbative matching kernel. And then there's power corrections that go with your distance squared. So this looks a lot like the formulas you'll see for phenomenological studies. We have something measurable that you can have data for on the left-hand side. And then on the right-hand side, you have the PDF convoluted with something perturbative. So you do have an inverse problem in this case. With the quasi-PDF method, you actually take a Fourier transform of your matrix elements, and this is what defines the quasi-PDF. And then this looks like a similar relationship where you have a perturbative matching kernel, FGG, convoluted with your Gluon PDF. However, this relationship is actually invertible because you're kind of working in like the same dimensional spaces, but so it's a little more complicated than that, but don't want to go into details. The power corrections here are in 1 over the Parton momentum squared. So with the quasi-PDF method, you can say pretty strongly like if our momentas are like 2 or 3 GeV, then you have good reliability in the range X about 0.2 and 0.8. So yeah, the main difference is just where you take your Fourier transform. The perturbative matching kernel for the top has a Fourier transform hidden in it, and the two matching kernels are kind of related via like a double Fourier transform. So the most modern calculations for Limette and pseudo-PDF method extend to meson distribution amplitudes, transverse momentum distribution functions, generalized Parton distribution functions. All of these have been calculated on the lattice. We don't just have like the perturbative matching for it. And many of these are not very well constrained by phenomenological studies. So in some of these cases, lattice is getting kind of ahead of the data. So we're waiting for like the EIC and stuff so we can see if we're right. You can look at this review here if you want to see like some of these methods. It's a little bit dated, but it's has a good overview. And that review was written by the creator of Limette, Zhengdong Ji, so it will be biased a little bit towards Limette. Speaking of biases, I want to talk about the politics a little bit. I want to inform everyone that there is like, there's kind of a clash between the two methodologies sometimes. And so to me, these are just systematic effects, and we just have to understand the systematic effects. Some people will speak about it a little more dramatically. So in the pseudo-PDF method, like I said, you have this inverse mapping problem from position space to momentum space. And that's not always very satisfying for your first principle calculations. We deal with it every day in phenomenology, but it's a little unsatisfying in the theory here. There have been many recent developments in like machine learning, Bayesian methods, and all sorts of fitting so that we can try and make this as model independent as possible. In Limette, you can actually, like I said, kind of get direct X dependence for your PDFs. However, you have to use some interpolation and extrapolation, all physically motivated, on your lattice data. And the pseudo-PDF camp you'll hear that, it's not as well understood by the Limette people as they claim. So there's some papers out there. There's kind of been a paper battle in the past year or two, which is pretty fun. But people will talk about this with their own biases. I'm trying to be a little unbiased here. So most studies focus on flavor non-singlet PDFs. For example, like the up minus the down for the proton, and then like the valence Quark PDFs for the pion. Because singlet PDFs actually mix with the matrix elements mix with gluon PDF matrix elements, which are a lot noisier and can dominate the signal and just make everything really noisy. So our group here at MSU focuses mostly on the gluon PDF. We find the gluon PDF interesting because the large X behavior, which is where lattice can contribute data to, is not very well constrained by the phenomenological fits. There's kind of a thing in the way here, but you can see in the large X that different groups with different parameterizations and stuff get all sort of different results because there's just not much data that constrains it very well. So Lattice QCD is starting to constrain our own statistical and systematic errors on our gluon PDFs and starting to contribute to phenomenological studies. So just a few highlights. We have the first physical continuum lattice nucleon gluon PDF. So that's the way that we are eliminating our systematic effects. We have gluon PDFs for the pion and the kaon. There's really not a lot of data, especially for the kaon, to get gluon PDFs from phenomenology. So that's somewhere we're almost kind of ahead. Hadstruct plus JAM solved the gluon helicity sign problem. So the data could have both plus or minus gluon helicity PDFs, and apparently recently, because of lattice data and high XDIS or something like that, they determined that it is positive. MSU plus CTEQ have recently put some constraints on the unpolarized proton gluon PDF. And all of these studies that I just talked about use the pseudo PDF method for the gluon. And so recently I put something on the archive where we got the first gluon PDF from Lamet. So now we have the two different methodologies and we can start understanding our own systematics and stuff better. And I wanted that to be super fast, and I think that was reasonably fast. So I'll just leave it there with the conclusion. Thank you.
Once you open the can of words about the Met and pseudo PDF, I mean, it's when you compare them, can you make quantitative evaluations of how they do, or?
Yeah, you can. It's hard to say because we're talking about, you know, regions where the phenomenological results are all varying as well. So sometimes you'll like coincidentally have overlap with one versus the other. So you know, just trying to use both methods and get them to, you know, be in the best agreement and understand all the systematics in each of them is a big challenge. So, I mean, it's not, I don't really think it's one better than the other. In fact, I think pseudo PDF is a little more suited for working with phenomenological results or phenomenological studies, because you can really just treat it like more experimental data and use the same framework. Whereas Lamet, I feel like you kind of, you know, you have to decide what parts of the PDF you're including and how do you include it, and you have to treat it differently. But sorry, that's kind of long-winded, but.
Other questions?
I don't think that, which benchmark, that we have, I don't know if you were saying that this is the difference. Maybe you can compare what's the difference.
Yeah, and I want to do that. Yeah. Maybe if anyone wants to say something. Okay. Yeah.
More about it. So QCD is kind of like very computationally intensive. So how do your predictions compare in terms of the computational review? There's like almost Carlos that uses not first principle model from where you think there's a divide in the payoff for using the lattice calculation that is really worthwhile to use lattice rather than Monte Carlo generation.
I think I don't understand a lot about these Monte Carlo methods. I think that's maybe next week what we're going to learn about. But I think in a lot of those cases, PDFs are the inputs to those. So
yes,
I may be wrong.
They definitely are. I guess in more general, I'm asking more in a general context of like other lattice,
Yeah.
not necessarily the yeah.
Mhm.
Yeah,
I think it's just, yeah. I think it's just satisfying to have first principles. Like if you can do it, you know, why not? But it's just me. Okay. Maybe if anyone wants 2 seconds, someone asked a question about alpha strong or had some concerns earlier this week. I wanted to go over one slide to explain my opinions on it. I'm not an expert. I had to read some papers real quick. But someone said, why are we using lattice in our global averaging for alpha strong? So I think what I read and how I understood is alpha strong is not an observable. Instead, you're actually obtaining it through phenomenological studies. You're combining theory and experimental data already for fitting alpha strong and ensuring everything is consistent. So my understanding is there's almost more theoretical and experimental assumptions going into those phenomenological studies than lattice QCD. And in lattice QCD, you put in like the bare couplings and stuff, but none of these things are directly related to alpha strong. So it should be in principle, you know, coming from first principles. You only have to put like 4 experimental inputs into lattice QCD to obtain results. So 4 experiments give you alpha strong, and you can't use those 4 experiments on their own to get alpha strong. So there's still probably some philosophical questions about whether we want to do that or not, but there's theoretical and experimental assumptions that go in on both sides of the studies. So yeah, so Alex mentioned scale settings. So like if you use 4 flavors of quarks, we take 2 of them to be degenerate. We take the up and down to be degenerate. So you have 4 bare mass parameters. Sorry, or I guess 3. Yeah. Yeah, pretty much. And then you have to set the lattice spacing. So in total, that's 4. You take 4 experimental inputs. It's just like renormalization. You have to fix it at some scale, you know. So thank you.
So that's all the physics for today, but just a couple comments for those of you that are looking to join us tomorrow. Oh. Oh. How did I, oops. Which one? 1, 2. Oh, did I? Oh, I'm sorry. I jumped, okay, thank you. All right, sorry about that. And we're still recording, so make this go away. And you're set, thank you.
All right, thank you. Thank you that I was not skipped. So, well, quick brief about me. I am Miguel Soto. I am currently starting my 4th year at the University of Kansas. And some of my research interests are actually neutrinos, dark matters, and in some quantum machines and quantum computation and machine learnings that may come in the way. So I will be talking about some dark matter. All we know that it's invisible, it reflects nothing, it acts only through gravity. There is no detection so far, no close proof of what it may be. So we may need to think of ideas outside the box to what this strange phenomena might be. So here is an idea. At the early stages of the universe, we have another false vacuum, we're gonna call the blank space on figure A, which has some really small points which we are gonna be calling the true vacuums. As the universe evolves, these true vacuums, the blue bubbles, are gonna be expanding. They expand further until only the blue dominates over the universe, which that will be the vacuum that we will be living on. But there may be remnants on this other false vacuum, that really small bubbles in picture B. So this is the idea of these kind of models. Something, 2 vacuums, one dominates over the other, and the idea is that these false vacuums may trap something underlying that may not let them escape. So we may have some dark fermions in our false vacuum. They may interact with this bubble that divides both vacuums. And some of them may go through the true vacuum, some of them may not. So once they are trapped in the universe, in this false vacuum, the universe expands, it pulls down, and there is absolutely no way for these fermions or particles to get out of this false vacuum. That's the idea of this phenomenon. But they don't happen, this is not happening for free. So there must be a U1 symmetry number violation between the phase transitions. There must be charge and charge parity violation. And there must also be out of equilibrium interactions once they are interacting between this wall, between the vacuums. The model that I'm working on right now is we have some fermionic direct fermions. They are coupling through some scalar under this U1 symmetry. They have their charge such that the symmetry is unbroken on our false vacuum. The singlet does not have a phase, does not have a vacuum expectation value on this side. So phase transition, it involves And this singlet inner to vacuum may generate a vacuum expectation value, which will allow for the symmetry of these U1 to be broken. And our direct fermions that we can in our false vacuum may go through, allowing us to have now some kind of Majorana direct fermions. So after the breaking, we no longer have directs and we only have Majorana fermions and some extra terms that are only evolved through some kind of mass diagonalization that occurs after the interaction between the bubble bonds. So they come through, they become Majorana, they expand, and the universe comes. This happens a lot. We are talking about millions of millions, so we will have to go through statistical physics. So in order to consider these phenomena, we will have to go now through the Boltzmann equation. So the idea of our model now is to study this Boltzmann equation through these Lagrangian interactions on the vacuums. And once we're able to understand and solve this Boltzmann equation, we may understand some of these properties of these Fermilabs, of these Fermi balls. For example, they may have some charge under this U1 symmetry. They may have some radius that we could measure, some kind of energy. And well, work is in progress under this stuff. Thanks.
So, I mean, it's interesting because you get various symmetry violations in these types of transitions. You mentioned the number of violations and things like that. So I mean, does that give you a handle on possible signatures or how might you?
So after this broken symmetry, this U1 is not the hypercharge from the standard model, it's another U1 symmetry. And once this is broken, it traps the particles. The only thing that may be measured in an experiment will be some kind of gravitational waves if they produce. And that's the idea of this kind of models, that we are only to be able to detect them through gravitational.
Is that related to the question of why there aren't equal amounts of matter and heavy matter?
You can make this yes, you can make those models through these kind of models. In this particular, on the direct fermions that I presented, it's not, but you can adapt it. Yes.
It's not as bad as that's the condition, the standard of condition. As soon as you have equal amounts, then you will form matter.
Yes.
But again, I want to ask you, thank you for the nice talk. The fact that you're considering, these are like disconnected cosmological horizons. Are you taking GR into a vacuum? Like, do you think of these as separated geometries in the universe? I'm trying to understand your first slide. When you maybe I don't understand this aids. Are these like disconnected regions, like geometrical horizons of the, or gated horizon of the universe?
I mean, yeah, it's kind of hard to explain how would you consider two vacuums.
Or maybe I also got another impression, like we're considering different theories value, like different Lagrangian description of the model that governs the dynamics in these different background or in and out of the background. Is that the idea?
So it's the same Lagrangian from which we're starting, but once they enter this U1 symmetry is the one that breaks. And it breaks due to the singlet due to the scalar that we add to our model, the phi. So in our unbroken vacuum, it has no depth, but once it goes through the symmetry phase, now it obtains a base and allows for the mixing to happen and allowing for the Lagrangian to offer some kind of transformation.
And then you don't need like any profitable and for space time, nothing like that.
No,
It's
anything,
not significantly breaking thing.
no, anything will be embedded into this sigma mu parameter. First order.
Let's thank all the speakers again.
Thank you.
Apologize for.
Yeah, no.
Yeah, thanks for. Okay. Yeah, and just some notes about tomorrow. Let me, for those that want to go to the Oldsmobile Museum, let me just map this out. So, directions, bus, and where it at. So basically from here, there are a couple options. Is that right? Friday. Oh, yeah, that. Not quite. Let's try that again. That's better. Okay, yeah. So essentially there are two options. You can either take a bus from this transit center and transfer up on Grand River. The bus fare is $125. You can use an app. I think I put it on the WhatsApp. I'll put it on again. You can use an app or you can pay cash. If you need a transfer, when you get on, ask for the transfer. They'll give you transfer. It's good for 2 hours, but not round trip. And then for those that want to go there, the signed up, we'll make sure we're there by 1 o'clock. So if you get there 1 or after, we'll have the tickets set up for you. That way, the cafeteria, if you sleep through breakfast, the cafeteria opens at 11, and you can get some lunch and then head over. And there are various places, nice place to walk around there. And then the jazz festival, which I'll get from Pavel and post that. I believe that starts 6 o'clock here in Lansing. And that is the schedule. So we hope you have a good free day. If you need to do laundry, there are pods there, and have a good free day. And then we will see you Saturday at 9 o'clock in the auditorium continuing. In fact, the first talk is an overview of FRIB. So that'll be particularly interesting. Yeah, question. Oh, okay.